In the last video, we talked about these 4 steps in formulating mathematical models based on theory of chemical and biological processes. In this video, we'll talk about finding model solutions, and we'll use our blending tank again as an example. The 4 steps in finding model solutions are to first find a method for solving the model equations, and then to validate the method and the solution. Then we solve the model, and finally, we interpret and apply the results. Until we've interpreted and applied the results, we have not satisfied our model objective. Finding a solution method can be very easy, or it can be very difficult, or anything in between. For explicit algebraic decoupled equations, this is simple. We simply isolate the dependent variables on the left-hand side of all of the model equations, and then we solve the model equations. And if the equations are decoupled, they could be solved in any order. Coupled equations may require reformulation and or sequencing in order to solve them directly. If coupled equations cannot be reformulated or solved in a particular sequence, they may need to be solved simultaneously. Implicit model equations need to either be reformulated or they will require a root finding method. For the simplest linear ordinary differential equations, solutions may be analytical, and it may be that you can find them using the dsolve function in MATLAB, for example. For more complicated or nonlinear ordinary differential equations and partial differential equations, often numerical methods are required. The numerical method that we apply will depend on whether problem is formulated as an initial value problem or a boundary value problem. Later in the semester, we'll discuss numerical methods for solving ODEs and PDEs formulated as initial value problems and boundary value problems. Finally, our solution method should ensure that all of the degrees of freedom are satisfied. That is, that we can specify all of the required NF. Let's look at the solution to our combined material and thermal energy balance for the blending tank. This is a linear first-order ordinary differential equation that can be solved analytically by several methods. For example, the I factor or integrating factor method. Here I've rewritten the model equation so that T3 and its derivatives all appear with their constant factors on the left-hand side of the model equation. I've also made some additional simplifying assumptions consistent with the example problem as it's described in the notes. T1 and T2, the two incoming stream temperatures, are the same, and so we call that temperature Tn. And we've also defined the time constant tau r, which is the residence time for the tank. Tau r, or the tank residence time, is m, the mass of fluid in the tank, divided by m.1 plus m.2, the total flow rate of the fluid entering the tank, which is also the total flow rate of the fluid leaving the tank. This enables us to cast this differential equation in a familiar form that we know the solution to. If we call the independent variable t3 y and the dependent variable t x, then we recognize this term in parentheses as the coefficient function p of x and the term on the right-hand side as the forcing function q of x. Then we can find the solution using the I factor method. We first need to find the I factor, or the integrating factor, which is e to the integral of px dx. This is simple since px is a constant. If we define the sum of the reciprocal of these time constants as the reciprocal of tau, then the I factor is e to the t over tau. Substituting these variables back into temperature and time for y and x respectively, we can now write the solution to the equation. Note that we have an arbitrary constant of integration because we've integrated with respect to time. That will be found using our initial condition. The second step is to validate our solution method and our model. Especially when we develop a new method for solving a problem, we should always validate the method. Method validation can be done in a variety of ways. One way is to check to see that the solution method works for a case with known behavior. If we've developed an analytical method, then we should compare that analytical method to another method that we know works, or use it to solve a problem that we know the solution to. Numerical methods can be validated by applying the numerical method to a problem with a known analytical solution. Once we know that the method is validated, then we should validate the model. Validating the model can be done by ensuring that the model predicts known behavior. Are there simplified limiting cases that we can apply the model to see whether the model works? Step 3C is to solve the model. This means assigning values or ranges for all of the parameters and independent variables to satisfy the degrees of freedom, and then using the method developed in step 3a to find the model outputs, that is, the values of the dependent variables over the domain of the independent variables. The solution may be single values for model outputs, it might be analytical equations describing relationships among variables, or it might be in the form of plots or tables. The final step is to apply and interpret the solution. This should be satisfying the model objectives stated in step 1a. The interpretation of the model may suggest that the model requires some revision. Often, modeling is an iterative process whereby we solve a simplified version, we modify constraints or assumptions until we arrive at a solution that meets our modeling objective. Here, we'll follow example 3.8 in the notes to apply our method to find a solution to the temperature of the fluid leaving the mixing tank. First, we need to satisfy all of the degrees of freedom by providing model inputs. We said that T1 equals T2, which equals the initial temperature of the fluid in the tank. We'll call that Tn, or T0. And that the heating fluid temperature begins at T0 and then undergoes a step function of magnitude delta Th. Here, the function h of t is the Heaviside step function, which is a unit step. It takes a value of 0 for time less than 0 and a value of 1 for all time greater than or equal to 0. Multiplying the unit step function, or the Heaviside step function, by delta Th suggests that there's a discontinuity in the heating fluid temperature. This could be because a pump is turned on or a valve is opened. The heating medium is initially at the same temperature as the fluid in the tank and then is suddenly increased by a magnitude of 150 degrees Celsius at T equals 0. We could use some other arbitrary function of time to describe Th, but we have to choose a function of time in order to satisfy the degrees of freedom of our model. We'll say that the mass of fluid in the tank is 1,200 pounds mass, and that the mass flow rates of stream 1 and stream 2 are both 150 pounds mass per minute. The characteristic time for heat transfer is set to 10 minutes, and we can combine that with the residence time for the tank, computed as m.1 plus m.2 over m, to find the parameter tau, which is approximately 2.9 minutes. Our I-factor solution, with these model inputs, says that T3 will be equal to T0 for all t less than 0, and will be described by this modified exponential for all t greater than T0. This solution is plotted here. To interpret the solution, we might want to compare it to one of the model inputs, in this case, Th as a function of time. We said that Th would start out at T0, and then at time equals 0, it would undergo a unit step of 150 degrees. When that unit step in the hot temperature occurs, the temperature of the fluid leaving the tank also begins to change rapidly. The temperature of the fluid in the tank rises, and it exponentially approaches a new steady state value. That approach to the new steady state takes about 10 to 15 minutes. This is consistent with the time constant of 2.9 minutes that we calculated. In this case, it isn't necessary for us to validate our solution method because we used the I-factor method, which is a known solution to linear first-order ordinary differential equations. But we should make sure that the solution makes sense so that we can be confident that we've applied the method correctly. An exponential should decay to about 63% of its final steady state in 1 tau, or 1 time constant, and to about 95% of its final steady state in about 3 tau, or 3 time constants. That's consistent with the rise to the final steady state shown here. In summary, Chapter 2 of the notes text introduces a detailed method for developing mathematical models of chemical and biological processes based on theory. We call these types of models theoretical models. And we introduced all of the steps in this modeling method using an example of a blending tank. I want to remind you that modeling is both a science and an art. Mathematical models should obey fundamental physical laws of the universe. The conservation laws, degree of freedom analysis, and other consistency criteria such as coordinate independence and dimensional consistency are required of all models. Other steps in modeling such as specific assumptions, selection of constitutive equations, and the method of solution, even how the solution is presented, provide many choices that the engineer can make. These are the artistic components of mathematical modeling. Again, I want to remind you of the aphorism from the statistician George Box. All models are wrong, but some are useful. Our goal is to produce mathematical models that are most useful for accomplishing particular model objectives. The steps presented here will help you to do that.